All right, everyone, welcome back. Section or part two of section 8.1. Actually, this is now a formula for the confidence interval. So we kind of talked about how a confidence interval is built, but that was a long process that we actually did pretty quickly. Normally, I would probably take longer, but now I'm just going to give you a formula. So the idea is once I select how many people I want to pick from the population, and then get the proportion of successes, I can then build a confidence interval. And there's a formula. It's very easy to get. It's very similar to the working the other way, actually, you'll see. So here's the formula. So a confidence interval equals p hat plus or minus. So p hat is the proportion of successes in my sample, plus or minus z times the square root of p hat q hat over n. So notice the p hat q hat over n is like the standard deviation, but instead of P and Q now, because we do not know P and Q anymore. Remember, we started the whole thing knowing P and Q to learn stuff, but we're never going to really know P and Q because that's what this confidence interval is for. And Z is a level of confidence. So Z is sometimes called a critical value. We get to decide what we want that Z to be. Based on whether we want to do a 95% confidence interval. So far, we've been doing 95% confidence intervals, which means Z is going to be 1.96. That's the critical value for a 95% confidence interval. You could do a quick little inverse norm. It's also a number you should probably know. We're going to use this number over and over and over and over whenever we use 95% confidence level, so it's worth knowing. All right. But sometimes mathematicians use 90%. Sometimes they use 99%. So what are the Z's that go along with those? We've already talked about these. I'm going to say use chart or calculator, right? 90% is 1.645, and 99% is 2.575. These are numbers we're going to use a lot. So they're just worth knowing. You can find them in the chart, or you can just do an inverse norm of 0.025. Sorry, that's 95%. If it's 90%, that means 5% on each side, right? So you do an inverse norm of 0.05. All right. A lot of times when we write a number, so when we do this, we're going to do an example. You'll see 45% plus or minus something, right? Whatever that Z times the square root of P hat Q hat over N is. That 3% is called the margin of error. Okay, so sometimes we specifically just say find the margin of error. It's how you see sometimes confidence intervals in the newspaper written are just, it's 45% with a margin of error of 3%. 3% is a pretty typical margin of error. We'll show you why in just a second, actually. These have been considered reasonably accurate. Mathematicians have done a lot of work with this. If these conditions are met, it's got to be a simple random sample, first of all. Okay, NP hat, and NQ hat both have to be greater or equal to 10. It's kind of just like the reverse of what we did before, but it's not P and Q anymore. It's P hat and Q hat. And the size of the population should be at least 10 times the size of the sample. If you start to take too big of samples, the problem is sometimes you can get dependent people. Okay, so typically we don't need a huge sample to do it. All right, so let's do a quick little example here. And then we'll talk about what it means and what we're saying. So here's my quick little example. In a simple random sample of 40 buses, 24 have a safety violation. Find a 90% confidence interval for the proportion of all buses with a safety violation. So I say check conditions, meaning have we met all the conditions? Those conditions are simple random sample, check. NP hat is 40 times, let me do a little math here. Sorry, the P hat is 24 out of 40, right? So 24 out of 40 is 60%, which is 24. And Q hat is 40 times 0.4, which is 16, both greater than or equal to 10. Check. And population at least 10 times 40 or 400. We don't really know that, so we're just going to check it off anyway. Most of the times, these conditions are formality for us because we're not going to know the population. We're just going to make the assumption that it's big enough. So let's do the confidence interval. So remember, here's how you build the confidence interval. You take your p hat, your plus, your minus, your z times your square root of p hat. Whoops, p hat. Sorry about that. You write a little bit neater. P hat q hat over n. So our p hat, remember, is the 24 out of 40, which is 60%, plus or minus, since we're doing a 90% confidence interval, that's 1.645 times the square root of 0.6 times 0.4 over 40. 0.6 plus or minus, let me do that little math, 1.645 times the square root of 0.6 times 0.4 divided by 40, 0.1274. So there's two ways to write a confidence interval. You can just leave it like that, 60%. Often we write in percents is better, so 60% plus or minus 12.74%, or somewhere between, I guess it would be 47.26%, and I hope I added that right, or subtracted right, 72.74%. Okay. So we believe that the percent of violations, buses that have violations, is somewhere between 47.26% and 72.74%. So we're going to talk about how we say that. That's it. That's all there is to it. It's really quite easy to do, but sometimes the terminology is a little bit weird and people struggle with it. So we're going to talk about the terminology and what it actually means when we say we think it's somewhere between those two numbers. So the way we refer to a confidence interval is, remember that when I do this confidence interval, I may be right, I may be wrong. The percentage of buses could be in there, but it might not be. So the correct way to talk about interpretation of a confidence interval is, it's correct to say that we expect P to be in 95% of the confidence intervals we construct. Okay, we're going to miss sometimes. Will we ever know if we miss? No. If you watch the election, they missed on some of them. They got some of them right. Okay. So it's not correct to say there's a 95% chance. A lot of people think the percent refers to probability. It's not true. Either we've already picked this sample, so either the proportion is in there or it isn't in there. Okay, there's not a percent. What that 95% chance means, again, is if I were to construct all the confidence intervals, it would be in 95% of them. And we're gonna do another problem and talk about interpretation when we go from there. All right, so moving along. One other thing before I talk about that interpretation is it's really typical. Remember, I said the 3% is typical because we can actually force the margin of error to be a certain thing. All right, so just think about the formula. P hat plus or minus z times the square root of p hat q hat over n. So if I take a bigger sample size, my margin of error is going to get smaller, yeah? Just math, it's in the denominator. And if I take a larger z, which means more confident. So think about 1.96s for 95%. But if I want to go to 99%, I go 2.575, right? So bigger z, more confident, but then I have to it's going to give me a bigger confidence interval. Most people don't want a bigger confidence interval. Most people want a smaller confidence interval. I could say, hey, I'm 100% sure that the actual population proportion of people who are there are safety violations buses is somewhere between 0% and 100%. It means nothing, right? So we don't really want bigger samples or bigger confidence intervals, but sometimes we get them. But what's kind of cool is like this. So what sample size should you use for a survey if you want the margin of error to be at most 3% with a 95% confidence? You can do this at any confidence level, right? So this is kind of predetermined. It's kind of cool, actually. So what we do is this. So we want the margin of error, which remember is my z, times square root of p hat q hat over n. So we want that margin of error to be 3%, no more than 3%. All right. So we're using 95%, which makes this a 1.96. Okay. P hat and Q hat, since you don't know what P hat and Q hat are going to be before you start, you can guess. It's totally legitimate to guess. But often we just use 0.5 and 0.5. If we don't know, we just use 0.5. That's the worst case scenario, actually, because you'll see the math behind this. If it's 0.2 and 0.8, my sample size will need to be smaller. So I want to make sure I get within 3%. This would be the biggest case. Now you just solve this equation for n. So I'll do a little algebra here for you. I'll write some of it up, maybe not all of it. 0.5 times 0.5 divided by n. Maybe I'll square both sides. Sorry about that. And then invert and multiply and do some flip-flop in. So let's go 0.03 divided by 1.96. I'm going to square that. And then remember, if I just, by the way, that number is a really, really small number, right? So we got some number here equals 0.5 times 0.5 over n, which means n is 0.5 times 0.5 divided by that number. So I'm going to go 0.25 divided by that number, and I get 1,067.11, which means I really need 1,068 to get within 3%. So typically, and we could change these numbers, that you could change the 3%, you could change the confidence level, right? This is very typical in election stuff. Typically, they just sample 1,000. You can see why they sample 1,000. That'll get you around that margin of error of 3%. But we can change those numbers. All right, so just kind of one last thing then, and we'll put it all together, and I'll be done. Whoops, that's not it. Let me go one more. So this is kind of putting everything together here, right? In a simple random sample of size 40, 28 said they had been to a fast food restaurant within the last week. Find and interpret a 92% confidence interval for the population who had been to a fast food restaurant within the last week. And then what is meant by that 92% confident? Because we hear that, right? And it's like, what does that mean? So I'm going to put it all together. We'll be done. So we're going to go 28 divided by 40. I know I could do that in my head, but I don't want to make a mistake. 70% plus or minus. All right, so now 92%. So now we're using a new number, right? The way you figure out the z, 92% leaves 4% on each side. So what I want to do is an inverse norm, or I could look in the back of the book, but calculator is really easy with 0.04 with mean of 0, standard deviation. Remember, that gives you the z-score, right? So I'm going to find that number here. We're going to go 0.04, inverse norm, the mean of 0, standard deviation of 1, and I get 1.75 times the square root of 0.7 times 0.3 p hat q hat over n, which is 40. 0.7 plus or minus 1.75 times the square root of 0.7 times 0.3 divided by 40. 0.12, I'm going to do a little rounding here. It's 67968, so how about we just go 0.127. Again, I like this better, 70% plus or minus 12.7%. I also like this, 58, so 57.3% to 82.7%. I was going to write that down because I'm going to need that on the next page, but I don't have a pen here. Maybe I do. There it is. Sorry about that delay. I'm just going to write this down because I'm going to use it on the other one. So 57.3 to 82.7. So now the last question was to interpret this. Like, what does this mean? This was the fast food question. And then what does 92% confidence mean? So we're going to go to my new little file here that says correct wording. So what does it mean? Correct interpretation of a confidence interval. So here's how you say this. If someone says interpret, you say I'm going to fill in the numbers for this problem. I am 92% sure that the actual population proportion, in this case, actual people proportion of the population who went to fast food. So there needs to be context, right? My blue writing is just more vague, right? The actual population proportion, but this is the actual proportion of people who went to fast food restaurant is somewhere between 57.3% and 82.7%. So if they ever say find and interpret, this is the interpretation of a confidence interval. And then the last thing is, what does it mean when you say you are 95% sure? And our problem was 92, so we can just change it to 92. There's two ways to say this. What this means is it's not a probability. Remember, it's not a probability. It means that if I were to construct all of the possible confidence interval, all of them, millions of them from this sample size, the actual population proportion will be in 95% of them. Okay, sometimes we're going to get it, sometimes we're not. All right, so if I were to construct, it's really important to hear this word, all of the confidence intervals, the actual population proportion would be in 95% of them. The book sometimes likes to write it like this, and some other people do, which is totally fine. It says if I were to construct 100 confidence intervals, the actual population proportion would be in about 95% of them. Notice I changed to about, and here's why. But the other one, it is in 95% of them. That's because we took all of them. If we only take a chunk of them, like 100, we would still expect it to be about 95% of them, but not for sure. We could get 0 of them. If you think about all the confidence intervals we construct, there are more than 100 of them that don't have the right answer in them, right? So if we happen to pick those 100, we'd get 0, but that would be pretty unlikely to happen in the real world. So I just have to throw in that word about. So the terminology can be a little bit weird. Finding the intervals, just use that formula and go from there. We'll go over some of these in the class next day.